Hey, hi guys. Let me just quickly start on this. Yeah, I think you guys is already aware of this. Today's topic is on sliding window. So on last times we have covered like very in depth on this binary search. So after this, this is a continuations of this. You know at what times you will be starting the sessions. Yeah, Harish. So we are starting it now only. So basically, I'm just doing some setups and system checks. So I think now I am good with this. So we will start. We will start like very shortly, Harish. So in just next 2 to 3 minutes, I am just going to start it. Yeah, so before that, like Harish and everyone's who are basically watching the streams, can you guys quickly confirms that uh, you guys are going to get the video and audio and screens, like these three things is must, right? So these three things are you are able to hear me, you are able to see me at least my face only, and apart from that, the screens that I am sharing, you are able to see it. Okay, fine. I think you guys are able to see. I got the confirmations from two peoples at least. So, yeah, like others also, please do confirm for sure, right? Let me just check. And also, guys, please share the live stream to your friend circle who are also like practicing the DSA and targeting for good top tech companies, so that like on the advantage of the live stream is basically you guys can get your doubts clarified in the stream itself. So you on videos you guys can put your doubts on the comment sections, and this kind of a very async process for sure. But here the chances you guys can clarified your doubts in the stream itself. So that's the advantage of the streaming. So that's the necessity, and that's the advantage, like who are basically attending the streams, they are going to get it, right? So please do, please ask like some useful comments for sure, and at more specifically at any part, if you are not able to basically understand on any of the explanations or any of the code that we are going to show you, then raise the points on that time itself, because then we will basically done a quick reiterations for this part for sure, right? Right. Yeah, so with this, I think now we are good to start. Uh, yeah, so let me just quickly check the setup very quickly. Fine. Yeah, we are going to get the things. Okay, I think the things looks good to me only. So mostly we can start now. Yeah, so today's agenda is we will do the sliding window problems that we have listed over our this uh, this particular uh, 1, 2, 3, 4. Yeah, so we will cover these four problems, but some of the problems is kind of need vary. So these hard problems are really basically build your foundations for sure, right? So and we will definitely solve these hard problems with the in-depth intuition. So there would not be any miss at all, right? Yeah, with this note we can now start it. So do I have the board created now? Let me just create a board very quickly. So yeah, I will share the notes to all of you guys after the sessions to the video descriptions, and the links of the problem sheet, the DSA sheet, and other details I think you guys are already accessing, and this is there on the uh, sheet itself, like on our last video descriptions and on these video descriptions also. So we can name it as sliding window. So our board is prepared, right? So let me just quickly check the writings over there. Space disk. Yes, so now we can do the writings also. So yes, the main things of sliding window, if I can give you a very high levels of what actually the sliding window is. So the sliding window, sorry, this should work, this fine. You can take a green pen. Yeah. So the sliding window, this is our the things that we are going to cover. So our sliding window basically giving us the advantage on high levels. What is the advantage the sliding window is giving us? So the sliding window is basically giving us when we have a problems, when we have a problems which resides on a continuous segment of a iterable data type. More specifically I have to say a list only, a array, a list, this kind of data structure. So when basically you are going to face a problems where in a particular contiguous part of an array, a particular window. What actually mean by window? So if I have an window of this, if I have an array of this, so let's consider this is my array. So on this array, if someone is going to ask me what is the sum of this particular segment, or more specifically, if someone is going to ask me what is the sum of every k size subarrays, so let's suppose they have given us a k equals to 3. So they are basically ask us to every 3 size subarray. So this is one 3 size subarray, this is another 3 size subarray, from here this is another 3 size subarray, and from here there is no 3 size subarray. So like this we total have 3 size subarray, and let's someone is going to ask us what is the maximum sum of all the 3 size subarray, right? So now on brute. So here guys, please focus on this particular part, because here actually we are building the intuitions what actually the slide, why we have to even learn the sliding window on the basis of this particular problems. You will going to get how actually sliding window can boil down any quadratic complexity problems to a linear kind of time complexity. So I feel you guys are very comfortable with the time complexity terms that we are going to use, because we have already a detailed video, and I have already shared the videos to you guys on multiple times on past discussions of us. So I guess you guys have already went to this, and you guys are very thorough about what actually the time complexity means. So on brute, what actually you guys can suggest us, what we can do? So we can run a for loop for I in range n, and then eventually we can start a loop for j in range from where I to I plus k, and we can take a current sum or running sum. We can start with 0, and current sum we can do plus equals to my array of j. And finally when after this for loop going to get terminated, we should have a answer variables, and we can do a maximize this answer to my current sum or the running sum, and finally after the outer for loops over, we can return our answer. So what is the time complexity on this? This is for sure a big O of n, and inside that we are running a big O of k. So if we have k equals to as big as 10 raised to the power 5, and let's suppose our big O of n cross k, so that is our time complexity, is going to becomes more than my 10 raised to the power 8, then it is straightforward giving me, it will going to give me a straightforward TLE. So that is when you just have to think once in sliding window, for sure. So on sliding window, on high levels, what we are doing, how it is going to help us. So let's suppose when we have computed our answer to a particular size sliding window, let's suppose this. Now on the very next iterations, what is my next sliding window? This is going to be my next sliding window. So are you getting what actually changed? Previously this is my L2R, and now this is my L2R. If I am going to consider its L dash R dash, so this is my window, right? So what actually changed? So some portions I have just eliminated, and some portions I just newly consumed. That's the delta. So do I have to recalculate this entire window again? I don't think so. We don't for sure. But what actually changed, that informations we should able to compute, because it's a contiguous portions. So in the contiguous portions, if we change some things, so what we changed, we have eliminated some things from the front, and consume something in the end, right? So that is the delta. So with this, can we try to reiterate our pseudocode? Can we try to reiterate or recreate our pseudocode? So now we know in the sliding window, it's basically a updated versions of 2 pointers only, or some guys also consider it's a 2 pointer also. So, but we have a separate video for 2 pointers, so we will create so where we basically focus on actual 2 pointers, which is actually going to get solved by 2 pointers only. But sliding window is a kind of 2 pointers approach only, that you can digest to your brain. There is no harm on this. So initially we can start our L to be 0. So that is our left boundary. So please focus on this part, guys. So that is where your foundation is going to be built, right? So that is where your foundation is going to be built. So now what we can do? Tell me. So we have a R pointer. So we have a R pointer. So R is going to move for R in range from where to where? So R is going to iterate till end, right? Now I can take a current sum not inside this loop. I can take it outside the loop. And now what we just learned, when we are preparing a window, by R pointer. What is our R pointer? So that is our R pointer. By R pointer we will always consume. So this is the node. So by R pointer we will do consumption. By L pointer we will do elimination. Right? So that is on high levels. You just have to digest. Now focus on the template. Here we are building our template, right? So that you can reuse across all the problems. So focus on this particular part, right guys? So here we are actually building our template. So here template. So this template, see guys, you guys will see the beauty. These templates we can use across multiple problems. So here we have a L pointer with starting at 0 and current sum as 0 only. Now, what we can do, by our R pointer, we will do consumption. By R pointer, we will do consumption. How we can consume? How we can consume? My current sum is going to become plus equals to something known as nums of this R. We have done consumption. Now, we have to eliminate something. What is the conditions? My window is going to be invalid. So when R equals to 3, and let's suppose we have this consumptions we have done, and when we are at this particular portions, so we are considering this window, right, where L has started initially with 0. So we are considering this whole window. Is this whole window at all valid, guys? Is this whole window at all valid, guys? I don't think so, because we have to consider a window of size 3 only, size k only, right? So then we have to do some elimination. So how we can eliminate? So when my size is going to breached, when my R minus L plus 1, that is the window size, is more than my k, oh, it's breached my k, then we have to do its reverse. So that is the template. You have to do its reverse. So here you have consumed. So current sum plus equals to something. Here we are doing current sum minus equals to, by which pointer we are doing elimination? Consumption we are doing by right pointer, and elimination we are doing by left pointer. We have eliminated, and we can move further. L plus equals to 1. Right? So that's exactly you have to write. So after this while loop execution has over, my L and R should hold a valid boundary. For sure. Right? Now let's check. If my R minus L plus 1 is equals to K, so that means it's holding a valid boundary. So that means my sum, the current sum, I have to take care to my answer consideration. So how we can do? Answer equals to max of answer, whatever the answer currently we have at, to maximize with my current sum. And finally, after the outer for loop got exhausted, we can return our answer. As simple as that, guys. As simple as that this template is. So the point of focus is by R pointer. That is the first point. By R pointer we are doing consumption. Second point is check the current window's validity. By this while loop we are checking this current window's validity, and here we are just doing on third, if the window is not valid, do the reverse. By R pointer do the reverse of this step 1. Step 3 is the reverse of step 1. So on step 1 we have consumption by right pointer. Step 3 we are doing elimination by L pointer. As simple as that, guys. Right? That is the template on high levels. You have to remember. Now there are two quick theoretical things I just quickly iterate to you guys. So on sliding window, on all the problems, the sliding window, in sliding window, all the problems are in two categories. Sorry, what happens? So the first one is fixed size sliding window, and another one is variable size sliding window. So these are two major categories, and out of this fixed size is kind of an easy one. And this variables one is kind of a difficult of its versions, right? That is the thing. So here on fixed size, what is the difference between fixed size? So on fixed size, the problems that we have just saw, the window size will be given to you given to you statically, will be going to given to you statically on the problem itself. But on variable size, window size, window size, window size will be will be changing based on the based on the based on the condition. So that's what this variable size sliding window is, kind of an advanced topic. Once you master this variable size sliding window, then you are in very good path to at least to crack any problems on sliding window, to for sure, in sliding window, to for sure. So that is on the high levels the theory that we have had to learn. Now we can just do as many problems we can solve. We have saw our template, we have built our theory, and now we can, as many problems you can solve, your foundations on sliding window is going to becomes more and more stronger. So now one point I just missed. So the time complexity, right? The time complexity, how it is you. So now you guys might ask me like, hey Shavik, like initially you told me if it is, if the time complexity is quadratic, then it is going to give me an advantage to become my time complexity to be linear. So why, how it is here you guys might have the arguments that, hey Shavik, here you are running another while loop. So that means inside a for loop you are running a while loop. So that means the time complexity again is going to be big of n cross k, big of n cross k. Is it? No, because this for loop is not going to run a size of k on every times. So here, for even here, it is going to run only once. It's just going to becomes from 3 to 4. When it is going to shrink, it's going to expand, it's do shrinking. When it's just expanded, it does shrinking, right? So then what is the exact time complexity, man? What is the exact time complexity? The exact time complexity is, in your array, our R pointer is visiting everyone. Our R pointer is visiting everyone to be once, to be at least once times. By my left pointer, every element is going to visit it at max once. So every elements in my array is going to get visited by at max twice. Once by my left pointer, once by my right pointer. Once by my left pointer, once by my right pointer. So the time complexity, when we are visiting every elements twice, my time complexity is going to become big of 2n for sure. Big of 2n for sure. Till now, the things is clear to you. Just give me a thumbs up, or give me a yes, understood. Anything. Just give me that. So that I can proceed further. I can take a note that till now we have just completed very basics, but base clear is must needed. Is it clear? Give me a thumbs up very quickly. Yes, are we getting thumbs up? Anyone? Raj, Harish, if you guys are still there. Monique, anyone? If you guys are there, then please quickly do a thumbs up. Anything? Anyone? Okay, one thumbs up. What about else? Anyone else? Okay, from Manik it's UD, understood. It should be US, right? Or it's UD. I'm not sure. Like, I'm asking only. Understood, right? Everyone else, get it? Get it right? Everyone's okay. Okay, fine, fine. Okay, and if you understood, then please also like the videos. If you guys are watching and things are going to get clear to you, do a quick like, share please, share to your friend circle, share to your friend circle, so that people's who are also on the same boat can take the most of it, can take the most of it. Please do the share, guys. Right? Yeah, so let's go further. So we will start with the fixed size sliding window only. We'll start with the fixed size sliding window only, because variable size sliding window is kind of an advanced and eventually, like, first times to understand a variable size sliding window, it's kind of a complex for sure. So let's start with the fixed size sliding window on the very basic problems that I have taken here. So maximum sum subarray of size k, what we just understood, right? So can we quickly do a implementation of it? Can we quickly do a implementation of it? Right? Those who are basically there, search maximum sum subarray of size k. I think that is not on the sheet. Search on maximum sum subarray of size k. Search the problems, you will find the gigs for gigs links, and there just jump on this particular problem. Right? That is the problems that we have understood. We have built our template with this only. So solve the very base first. So in the problem statement, they have given an integer array ARR and a number k. Return the maximum sum subarray of size k. Right? The exact same problems. So now here you can see the k is hard coded. The k is given to you statically in the problem statement itself. So that means what actually it means. So it actually means that you should you should don't have to move your sliding window. Your sliding window size is static. That is fixed size sliding window. Your sliding window size is static. Your sliding window size is static, right? That is its means. Now, can we do quick implementation of this? Can we do quick implementations of it? So on the example test case, I think the problem statement we will not have to do that much brainstorming. So that means here you can see k equals to 2. What is the maximum sum subarray we can get? That's 300 and 400. That array of 2 and 3. 0, 1, 2 and 3, and we will get the 700. K equals to 4. 1, 2, 3, 4. 0, 1, 2, 3, 4. This window they have taken and they have got the sum of 39. K equals to 1. Single window 400. They have vended out 400 on. Right? As simple as that. Can we try to write the code versions of our template? Can we quickly write the code versions of our template now? Yes, man. Yes. Let's do it very fast. Let's do it very fast. So I have to start my n should be my lane of ARR. Then what else we need? We need a running sum. We are doing live coding, guys. We are doing live coding for you guys. If at any particular lines, any doubt you guys have, please ask right away. Every variables, everything I am initializing, writing, I am basically doing it with the verbals also, so that you guys also going to understand why I am basically doing these things, right? We need a running sum. We have defined our n to be len of ARR. What else we need? We need a answer variables for sure. What else we need? We need a left pointer for sure. Right pointer Shavik. We will do by our for loop. Itself. The for loop variables we can consider as our right pointer. So right pointer don't need, for at least for now. If needed, we will initialize. Running sum to be 0, current answer to be 0, left pointer should also at initialization should be 0. Now for r in range n, so by our for loop, our right pointer is going to be covered. What we have to do? First we have to do consumption. Running sum plus equals to ARR of R. we have done the consumption. Clear, right? Till now clear, everything is clear, right? Running sum plus equals to ARR of 1. Now have to check the validity, of the window. If R minus L plus 1, that is the window size, is more than my K, the window, man, is invalid. Window is invalid. Shrink your window. So if we have to shrink, throw our L pointer consumption, we have to eliminate from my running sum. How? Minus equals to just reverse of this particular line. Just reverse of this particular line. See, I have just copying it. I am just pasting it. Like this, you have to remember the template, guys. Reverse of plus is minus. And by R pointer, we are doing consumption. Elimination, we are doing by left pointer. Done. Reverse is done. Move your left pointer. Done. Yes, we have done. Now, if the current window is valid or not, how we can check? If my R minus L plus 1 is equals to K, so that is the window is of size K, then consider this answer to be your candidate of your answer. How we can do? Maximize your answer to be answered with running sum. Yes, as simple as this, as simple as it. Finally, we can return our answer. Should we do a quick compile? Yes, we can for sure. It's compiled successfully. Can we do a quick submit? Let's do a quick submit. Yes, and indeed it's passed all the test case, and it's giving us a for sure shot accepted. Right? Clear, right, guys? The first problems we have solved with the fixed size sliding window is clear to every one of you. If it is so, then please please like the video, share the video first, and then put the understood. Do like, share. Can you explain it with a dry run? Oh, Rajan. Yeah, Rajan. We actually have the dry runs. I think you have joined late, man. So we have done the whiteboardings here. So here basically what we are doing, I'm just going to reiterate to everyone's to on very quickly. So let me just reconnect the things. So what actually we are doing, Rajan and others also who actually not able to digest the code on the very first book. So slide on this sliding window, what we are actually doing. So we have to basically take a K size sliding window, right? We have to take a K size sliding window. So on the K size sliding window, by R pointer, we are doing the consumption. So let's suppose we are with the dry runs. Let's consider we having this. We have these things. We have this particular example test case. Now someone is asked me for K equals to 2, give me the maximum sum subarray. So by brute, what we will do for every particular index, we will start a K size loop. But on sliding window, what we are doing, we are basically stating first build a K size sliding window. So it is applicable for fixed size sliding window on. Now move your window by your consuming by your right pointer. So we have consuming this 3 to my window by moving our R pointer to be consumption. Now the L2 R, the window, the size is we have breached it. Right? So now what we have to do, we just have to shrink our window by moving my left pointer to be right. By throwing away these particular elements from my answer. So on very first go, our answer is coming to be 3. Next window is going to give my answer to be 5. Next window is going to give my answer to be 7. Next window is going to give my answer to be 9. And out of this is the maximize. List is very helpful. Thanks a lot. Okay, Rajan, is it clear now? So that is on the high levels. That is on the dry runs. How actually our window is going to be shift right by consuming right pointer and by eliminating the do the eliminations by our left pointer. Do the eliminations by your by our left pointer. So here you can see I have basically provided the template we have already explained. So I will definitely suggest to basically go to the this particular OneNote sections of the video of the streaming, so that you can get the gist, and post that you can do the first forwarding. You can watch it in 1.5x or 1.25x to basically quickly catch up us. But yeah, I think for now it's clear to everyone, right? So we have solved our very first problems with the templates that we have built with this. By the right pointer, we are doing consumption, right? And by left pointer, we are doing elimination. And when we are doing the eliminations, when our window is not on the correct path, our window is breached out, our window is invalid, we are doing the elimination by our left pointer. Clear to everyone, I guess now, right? We have done two to three iterations what we have just did. Now just we can start on the this particular sheet. So I have opened the problems to basically quickly do it. So these four problems, 1 2 3 4, yeah, these four problems, that is the discuss sections that I can close. So these four problems we have to solve, and let me just quickly validate for some 1 2 3 4. These four problems we have to cover on the sliding window, right? So now this is the first problem. So these problems we will going to get the feel of variable size sliding window. So majorly the problems are residing on variable size sliding window only, because the reason is variable size sliding window is the topic where actually if you are preparing the interview for top product companies, at least for MAANG level companies, you should be very prepared with the variable size sliding window, because the fixed size sliding window is very basic. We just have our window size is constant. By one pointer a single consumption happening, and by left pointer a single elimination is happening. So it is a kind of very straightforward. But this variable size sliding window is kind of a indeed difficult, and indeed focusables, I have to say for sure. Indeed focusables, I have to say for sure, right? So here given a string, we have given a string s. Find the length of the longest substrings without duplicate character, right? So here you can see we don't have any k pass, so we can't predict what is the window size we have to consider. With this we will get our answer. We can't, because here actually the window size people is basically ask us what is the given a string is find the length of the longest substring. So that is our longest window. That is the longest window. What is the longest window, man? You can build it with which actually satisfies the conditions. Longest substance without duplicate character. So here you can see this A, B, C is valid. But when I just consume one more A, this becomes A, B, C, A. So the on the current window, there are duplicate characters. There are duplicate characters, right? There are duplicate characters. So I think the problems in one liner is very straightforward. I think you guys should get the concept in very first go, right? Everyone's just go to the problem statement, and if at any part if you are not able to understand the problems, put it on the chat. But this particular problems, I am not expecting anyone's to be asked what actually this problems means for. It's very clear to you. It should be very clear to you, right? So now start with our template, and we will eventually see how we have to do slight modifications to our template to basically get an AC for this particular problems. Let's start to our template first, right? Let's start with this. So what we have, tell me guys, what we actually have here, tell me quickly, what we actually have to our template. Prince. Sorry. So on the template, we need in, we need our left, right? We need an answer. These three things though on very initials I can think. Very initial I can think. And to basically check the duplicate, we need some frequency map. We need some frequency map, frequency characters where we basically store the count, of it. So we need a dictionary. I can name this as default dictionary. So these data structures on very first go, by seeing at the problems, I think we definitely need, right? So now quickly initialized everyone. N should be my len of s. What else? L should be 0. Answer should be 0. What do we have to do? Return the longest. So we can start with some minimum value to be 0. Answer we have done. DD to be my default dict of int. As per your language, it can be a hash map for Java. For others, it can be a map. Data structures you can use. Unordered or ordered map, if you are in C++, you can use accordingly, right? So now what do we have to do? For R in range in, that is our very standard template. By right pointer we will do consumption. If we are consuming this particular S of R, then what actually we are doing, meaning by consumption, its frequency is going to be increased. The dictionary that we are following on the sum problems, what actually means by consumption? We are carrying a running sum, we just have to add it to my running sum. What actually means by consumption on this particular problems? The frequency of this particular characters is going to be increased to my dictionary. That is the meaning. That is the meanings by consumption, right? So I can do plus equals to 1. Now we have to write. Here we have to write. So this part I am again writing in kind of a template only to you guys, so that you guys can get it. Here we are doing the consumption. Or expanding our window by doing the consumption. Now we have to write our very favorite while loop. On the while loop, what is the conditions of the while loop? If my current window is invalid. If this is invalid, then we have to do the shrinking. So what particular characters I just ingested to my running window? I don't know what is the size of my running window, but it is present by my dictionary, right? So I have just consuming in my dictionary a S of R, so its count going to become more than 1. So the current window is invalid due to this particular character consumption, right? Because that's exactly we just do now. If this particular window is going to be invalid by this particular consumption, what is the invalidity then? Can I write it? If my D of S of R, this particular character's count is more than 1. Yes, ma'am. That is the invalidity conditions, because here they have written very thoroughly every character should be present at least exactly once. Not duplicate allowed. No duplicate is allowed. Right? So if my D of S of R is more than 1, so that means this characters becomes duplicate. Then shrink the window. Window shrinking always happens to be by left pointer. Then D of S of L, for shrinking we have to do minus equals to 1. So this should be DD. So here we are doing elimination. Here we are doing elimination, right? We are moving our left pointer to be L plus equals to 1. Clear, right? This is the foundation. This is the foundations of variable size sliding window. You have to decide your so these conditions here also I am writing the doc. Window invalidity, shrink until your window becomes valid. So that is the point. This variable size sliding window is challenging because on the past problems you remembered we have a very standard logic, r minus l plus 1 is more than k, then we can shrink. So the static window size they have given to us. So that's the basically advantage. That's the basically advantage of or the easiness of fixed size sliding window. But on variable size sliding window, you have to shrink your window based on the dynamic conditions, until your current window is invalid. Until your current window is invalid, you have to shrink to make it valid. Shrink until your window becomes valid. That is the things that you have to remember. Now what else pending? So with this, can I do my answer equals to max of my answer and r minus l plus 1, that is the window, and finally I can return my answer. If things are good, it should work. DD, right? Should be DD. Yes, it's passing the sample test case. Can we do a quick submit over there? It should work, guys. If we written yes, it's indeed an accepted. Yes, it's indeed an accepted. Right. Understood. We have solved a variable size sliding window problems also. Time complexity I am not going to reiterate to you guys. It's big of 2n only. Every element is going to be visited at max twice. Once by my left pointer, second times is going to be my right pointer. First times is going to be my left pointer, second times is going to visited by my left pointer, right? It should become crystal clear to you, to your brain, right? It becomes crystal clear to your brain. If so, can you please put a like? Quick share and subscribe if you feel the things is helpful to you. Do that, please, right? So with this, we can take a quick break for 5 minutes. But before we are going to go to the break, I am just going to give you the next problems. This is the hard problems that we are going to solve just by next. That is for sure based on the variable size sliding window is bound to be, and this is LEED code 76. Minimum window substring. You guys can take your time, find the problems. This is already in the DSA sheet that we have shared. You guys can find the problems and then eventually read it. And if you have any doubt, put it on the comment sections, put it on the chat, live chat, We will reiterate the problem statement. But before of that, first do the first levels understanding and try to make your brain to think some things before we will start, right? Please start some hands-on. Please try to do some hands-on. Whatever you are able to write, please try to do. And we will be back by 2025. It's 2018, so we will be back by 2025, right? But guys, please do these things before we are back. I am assuming when we are back, you guys have the understanding at least of the problems. You guys have understanding of the problems for sure, right? With this, I am putting the BRB. And if you have any doubts, put that on the comment sections, on the chat, right? Hey, hi guys. Yeah, we are back. I guess you guys have went through the problem statement, right? Have you guys went through the problem statement, and is it clear to you? Is it very clear to you? I'm not expecting any not understood at least on the problem statement for sure. That I'm not expecting, because this is an hard problems, and if you are here to basically solve these hard problems, then this particular problems understanding I'm not going to basically hoping any doubt on this, right? Now let's quickly start on this. So this is a kind of a problems where actually we have to do a very, so this is kind of I have to say a master level problems of variable size sliding window. And if you are able to solve these problems, and once you have digest the templates of these particular versions of the sliding window, then you will never going to be at least do this sliding window problems. You don't have to basically bother at all on any interview perspective. There is not more than difficult problems is exist at least on the sliding window. I have to basically do the insurance of my knowledge, right? Yeah, so given two strings s and t of length m and n respectively, return the minimum window substrings of S such that every characters in T, including duplicates, is included in the window. If there is no such substring, return the empty strings. Return the empty strings. So initially they have given to us two strings s and t, and we with length m and n, and return the minimum window substrings. What actually mean the minimum window substrings of s? So that is a substrings of minimum window. I think minimum window words is very clear to you. Substring is also bound to be clear. Contiguous part, we are already playing the entire game. Sliding window basis based on continuous part only. So such that every characters in T, including duplicates, every character in T including duplicates is included in the window. Included in the window. If there is no such substring, so this is a parent string. Is you can consider is a parent string, or kind of a superset string, and T is going to be the child of it. T is going to be a child of it. So here you can see, but not exactly ABC. Ordering does not matter. So every characters of T, every characters of T, the frequency of every characters of T should match the substrings that we are going to consider in S. So on S we have to cut a piece, cut a slice, cut a piece, right? Which actually going to just map with going to the frequency of the characters. Ordering does not matter. Ordering does not matter. Where which particular terms I am repeating, right? That particular terms is actually important. Focus on that particular terms. So you guys are solving a hard problems in a live stream, and I'm explaining to you guys in live. So this is for sure a master level problems, and you guys are getting the opportunity to get the understanding on the live stream. So please be focused on this particular terms, things that I am explaining. The every particular words that I'm repeating, there should be a meaning for this, the repetition. So on this particular example only, if you just iterate this particular example, you can see this particular ABC. We need any ordering of ABC in S which is minimum in size, minimum in size. So here you can see they have written this BANC, BANC. BANC. So every A is present, yes, A present, only single occurrence. B is present, yes, yes, it's present also with single occurrence. C is present, yes, it's also present in single occurrence. But they can be multiple, but they should have at least there the requirement that the count of occurrence in T, that count should be present of that particular characters. But more, we are fine. More, if there are multiple B's in this, that also fine. So that's the reasons they have mentioned including duplicates, right. And this N, you guys may argue, Shavik, this N though is not present at all in T. Fine, right? They have just want to find any slice in A's, any slice you can give them to, which has at least the characters which is present in T with the frequency in T. The frequency of A in T is 1, frequency of B is T in 1, frequency of C in T is also 1. So they just look to a particular slice which have at least one A, at least one B, at least one C. More than this, fine. Other characters, fine. So they are good with this. So that slice you find, you have to find from this S, and you have to just give to them. Other characters occurrence, also fine. So like this way, what is the minimum slice you can give them, minimum slice window you can give them, that exactly they are looking for, I think now it bound to be clear. Is it clear, guys? Is it clear? Is the problem statement is clear to you? This S and T, very straightforward, they have returning A. This A and A, so here you can see this particular T like has two A's, but S doesn't has two A at all. So here you can see we have to return it empty strings. Is it clear? Is it clear, guys? Just quickly gives an heads up if the problem statement is very clear to you. And here you can see our M is very big, M and N is very big as 10 raised to the power 5, and S and T consists of upper and lowercase English letters. So this is consists of uppercase and lowercase English letter. Follow up, could you find an algo that runs in big of M plus N time? Could you find an algo that will run in big of M plus N times? Can we get an understood at least the problem statement, what we have to basically given to them? Do we have an understand? Everyone understood, right? Okay, we got one understand. I am assuming like if there is no response, then I by default I am going with the yes only. You guys get it, right? Yep. So yeah, so now let's just think about what we can do here, so can we start with our template first? Can we start with the templates that we have built? So here, what actually my targeted window, here also we need the frequency of all the characters in the T should be my targeted window, right? First you have to, so when this is a variable size sliding window, you first have to decide your target. So our target is variable, our target is occurrence of all the characters in T, so can we build our target then? So we can define our N and M to be len of my S and len of my T, right? What else? And then I definitely need a default dictionary, or I can go for a dictionary altogether, DDE, and this should be a simple dictionary at all. So these things, so we know for sure, and by default what we need an L, we need an L. Yes, left pointer we should start with 0. So before we start, we definitely need a frequency of all the characters in T. So that should be my statically present before we start at all my sliding window at all, right? Before starting my sliding window, the expansion and shrinking, the expansion of the window and shrinking of the window is depends on the count of characters in T, frequency of every characters in T. So that should be by default present before of sliding window starting. That should be present in my hand, right? So can we quickly build the frequency map? Yes, for each in T, right? For each in T, then dd of home, dd of, here we are using normal dictionary. If my each in dd, then dd of each plus equals to 1, character increase. Else, this is the first key, so dd of each we can initialize to be 1, Is it clear? I hope so. Tell me guys, it's clear, right? We just have to initialize our dictionary. So now we have the requirements. So more specifically, I can name this as a target. So this dictionary is my target. Right? This is my targeted dictionary. So targeted dictionary means, or requirement dictionary, more specifically we can say it. So this is my targeted dictionary or requirement dictionary. So what actually it means, in my window or the targeted dictionary, what actually it means. So that means if my target of each is present in the dictionary, then when we are basically expanding our window, so this many occurrences, this, let's suppose target of each is, when we are building this, A's count is 1, B's count is 1, and C's count is also 1. So that means we need at least 1A, at least 1B, at least 1C. So that is our requirement. That is the frequency map of requirements. We have built it. Now with this, let's try to fit our template. Our template should be for R in range. Now with my right pointer, what should we have to do? Quickly tell me. If that is in the requirement, so we will consume, right? So before of that, we have to check if my S of R in my target. So that means we have a target of it. We have a target of it, right? If we have a target of it, then we are doing its consumption. We are basically, let's suppose we have 5 A's needed, and by moving our window, we got 1A. So our requirements is going to be decremented by 1. So my target of S of R is going to get decremented by 1, because I just found one of the requirements character, and I am just consuming by my S of R by expanding our window, and its requirements got satisfied by 1. Now when I can say, so let's suppose we are consuming, let's suppose there is 1A is needed, right? 1A is needed, but let's suppose we have consuming 2A, so as it is my S of R in target, right? S of R, the A is in target, so we are going to run with negative. So negative at any point in my S of R means that we have we have over consume. We have over consume. So here we need that many consumption, that many consumption, that many consumption. So here you can see, rather than initializing m here, if I can initialize my m to be here only, then it will make to you guys a little more sense. So that means when I am also increment my m counter, so m means that many characters is present in my t. So that many consumption, that many consumptions bare minimum you have to do, that many consumptions in bare minimum you have to do. So now if I am going to check if s of r by this consumption that we did, if target of S of R, the consumption that we did by this consumption is more than equals to 0. The consumption we did here, right? We have let's suppose 2 requirements of A and we consuming 1. Next, again we found 1A, we have consuming another one. Then my target of S of R just becomes 0. So until we have requirements of S of R, how we can find this particular characters, the window that we are considering is in the requirement, that is going to be went by this target of S of R. If it is more than 0, so that means we have requirements and we done consumption. We have more requirements and we have done consumption. We have requirements and we consuming in parity with requirements. But there can be cases, let's suppose we got 5 consecutive A's and we have requirements of A of 2. So 3 A's are going to be over consuming. The 3 A's will going to becomes over consuming. So for this, if my target of S of R more than my 0, so that means it's a valid consumption. So here we have requirements and we done consumption. So my M count is becomes negative out. My M count is becomes negative out. So whenever we have do the, so M is basically storing that many altogether bare minimum characters you have to consume. So this is the size of my T altogether is stored in M. So when we have to decrease the count of M, so here we just understood, right? On the target, we are going to become negative by do over consumption, right? So if it is over consumed, then we have to negate our M to be minus equals to 1? No, right? We don't have to negate our M because here we are doing over consuming. We have consumed more than my target. So M should not go down. M should be lies from 0 to M value only. It should not go more than like less than my M, because when we are over consuming, my target dictionary should go into negative, but M should only down when we have a valid requirements and we done the consumption of this particular characters when we have requirements. I think it should be clear with these explanations after this. Now we have done consumption. Now when we can shrink our window, can this M be a deciding factor? Can this M be a deciding factor? Yes. If my M is equals to 0, so that means we have consuming that many characters, we have consuming that many required characters. Now can we shrink? Can we shrink now? So this means we have consuming sufficient characters. We have consuming sufficient characters. The M value is basically pointing that many characters, so we need. We have consuming with parity with the requirement. We have consumed with parity with the requirement. So when we have requirements, we have consumed. So that means when we have this M value to be 0, so on that times you might be consuming some, you have done some over consumption. So now can we shrink your window? Can we shrink your window to basically do in a minimum threshold? I understood you might need some over consumption. So on this particular example, you can see N is an over consumed element. N is an over consumed element, right? So I understood. If you have some over consuming, I find, but let's try to shrink. With but your target should be M equals to 0. Your target should be M equals to 0. You should not consuming when you just bump up an M count. When there is a requirement, you don't have to shrink, then you have to expand. But when you have m equals to 0, you have done the entire consumption, you can shrink, you can shrink. Let's do shrinking. Let's do shrinking. How you can shrink? If I can just copy paste, so that is the beauty. I have already give the beauty, already give the template, how you have to use the power of the template. That's the beauty. That's beauty I have already taught you, right? That beauty I have already taught you. So here you have just do the reverse. R, do reverse of S of L in target. Target of S of L, now it's going to become minus of plus. We don't have to think at all, man. We just have to reverse, because on the consumption, elimination is just opposite of consumption. And if my target, here the condition change. When so this particular characters, when we have to say there is a requirement, just arise. With this elimination there is a requirement come. With this elimination there is a requirement come. When we can say, when my is of this particular characters, when we just have eliminated it, and its requirements is becomes more than 0. If there is a positive requirements, if there is a positive requirements of this characters is bump up to my target, then we have to do m plus equals to 1, m plus equals to 1, because with this elimination, the requirements of this particular characters is regenerated, the requirements of the particular characters is regenerated. So m plus equals to 1, right? Like this way, I think we have to move our L pointer to every time L plus equals to 1. Yes, these things we just have to do. Now what they have asked the substring. So where actually we have the substrings. So on this particular while loop only we have the valid substring, right? So if what we need minimum. So r minus L plus 1, that is the window size, is less than my size that we are already considered, right? If the window size is less than my the size that we are considered, then L, R and size, we have to do something with this. L should be my, sorry, it should be my left. So we will do some, we have to return the final substring, right? So we will do left to right slicing, left to right string slicing we will do. But first, by the sliding window, we have to set our left and right to be correctly. So my left and right should be my L and R, that is the window that we are currently considering, right? And my size becomes R minus L plus 1. Yes, that is my size, is going to becomes. Let's quickly initialize those. We need a left, this left, we need a this right, and we need a size. And we can initialize left to be -1, right to be -1, and my size to be, let's consider a very big value. What is the maximum window size? Is 10 raised to the power 5. So 1 2 3 4 5 and then 1. So that is the maximum, like the constant they have given. We are like max of, like top of that only, right? So now we have done shrinking. Do we need to do anything, or we are good here? I think we are good here for sure. Finally we have to check if my L is equals to -1, sorry, not L, my left is equals to -1. So that means we didn't find anything. We can return an empty strings, else we can return a is of left to right plus 1. If we can return this, it should work. Yes, any doubt guys, any doubt on any particular problems, any particular sections, any doubt? Let me just quickly do a compilations of this. Too many value to unpack. Okay, what I did here, left dot happens. If any part you guys didn't understand, please do the chattings now only. Okay, m I have to initialize, m should I have to initialize to be 0. If at any particular points you guys not able to understand, please do the live chat now only, because we are solving the master versions of sliding window in live with the streaming to you, all of you guys. Every lines we have done the explanations why we are writing this. It's successfully compiled. Can we do a submit? If it is going to be an accepted, it becomes a booming for sure. And yes, indeed, we are beating 92% submissions over the lead code, and it's bound to be the most optimized. What was the follow-up? If you guys remembered, we have to solve it in big of m plus n. Is our time complexity is big of m plus n? Let's check. Analyze. It's big of n only, so that means big of n plus m for sure. So but yeah, like it's big of m plus n that we are solving it linear only. Is it awesome? Is it awesome, guys? Is it awesome? Is it on the next levels? You have solved a master versions of sliding window with the template, the basic template that we have understood. With that basic template, you have solved the master versions of sliding window in the live streams we have solved. And any doubt, I am just going to check if any doubt is in the comment. Okay. Okay, Rajan, like this basically not on language specific. Sliding window is not a language specific things, man. No matter like which languages you are writing, you can just copy the code. Maybe I will share it, and you can just use some AI nowadays and get it converted to C++ or Java, the language you are comfortable. So that you can do for sure. But on dry runs, there I don't think so any dry runs is needed, Rajan, at least, because here we just have to use our own template and we are doing the same game that we have initially did, right? We have by our right pointer here, you can see by our right pointer we are do the consumption when we are consuming. If we are just checking if we are in the requirement, we are doing consumption in the requirement, then we are basically eliminating the total max level requirements that we have, total requirements we have. So if this is the characters that is there in my target list and we are consuming within the boundary, then we are reducing its count to be m minus equals to 1, m minus equals to 1. So that means we are doing a valid consumption. We should decrease its character count, its requirement count on the high on the high part, on the total part, total size part, on the total size part. Else now on the while loop, we have to, when my m becomes 0, so that means we are in the boundary where we have consumed every requirements. Now with every total requirement consumptions, can we shrink? Every total requirement consumptions, can we shrink? That's exactly we are checking. So here we are doing the shrinking phase. So here we have done the shrinking here, just copy pasting, done the reversing, and we have done with the shrinking part. And here we have just basically created those to build our answer. Finally, we have to slice from left to right plus 1, basically left to right only, to return the answer. And if L left is pointing to -1, so that means we didn't find anything, so return -1. That is the template on the high levels. I think it's bound to become clear to you guys. It should be with that levels of explanations, that levels of clarifications, the last 2 to 3 continuity of the problems. If you have already there with us, then you should get it. Like Rajan, let's not take it on different note, because like dry runs, it's not going to help at all, like to at least on the understanding this particular problems, because every problems have its every algo every problems have its own way of understanding we have to do. So if you have understand the templates on the high levels, the templates dry runs we did, if the templates dry runs, if you are able to understand on the high levels, then you are on the good note only. You are on the good note only. You don't have to do the dry runs of every problems by doing the dry runs. You will not get any extra gist which we have done with the line by line code iterations. So that should be more than sufficient, at least for my point of view, right? And if you are able to explain with this much clarity to on any interview, this is not specifically to Rajan, it's specifically to everyone's. Like if you are able to explain this to that much clarity, then like man, you are in the very good boat to basically crack on any interview where you are basically facing these sliding window problems. Right, with this note we can go further. So the next problems is another hard, but I let's not like go away from here, because these problems I have to say is not that much hard that we have just solved, but it's also a very good problems to solve, right? But this is not that much hard versions that we have just solved, but it is also a very good problems to solve. So on this particular problems, we will quickly do the like problems understanding first. So we have a sliding window maximum now. So what we have to do? So now in the problem statement, they are given an array of integer nums. There is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one positions, return the maximum sliding window, max sliding window. So here you can see on this example test case, 1 3 minus 1 minus 3 5 3 6 7 k equals to 3. So we have to consider every 3 side sliding window. No questions, right guys, from you guys side? Things are clear, right? If things are clear, please do a like, subscribe for sure. I am basically trying my best to best. I am putting my best to best effort to explaining to all of you guys like the very toughest problems of the sliding window we are doing in live, and I am taking any doubts if you guys have. So I think we deserve some likes and subscriptions for sure. Please do some awesome likes, and please do some comments that you are going to entirely get the gist what we are doing here, right? Please do some likes, and please do the subscriptions, right? Cool. Thank you guys, thank you so much. So now we can go further. You can only see the k number. So here you can see on this example test case, so the first window is 1 3 minus 1, 1 3 minus 1, first window. And what is the maximum of this? 3. So we have written this 3. Next window shift with 3, window shift by right with 3 sides. 3 minus 1 minus 3, max is 3. Window shift minus 1 minus 3 5, minus 1 minus 3 5, maximum is 5. 1 3 minus 1 minus 3 5 3, maximum is 5. 1 3 minus 1 3 5 3 6, maximum is 6. 1 3 minus 1 3 5 3 6 7, maximum is 7. So final list we have to return 3 3 5 5 6 7, 3 3 5 5 6 7 that we have returned, right? That is the problems. You have to take a window of size k, and you have to basically move your window by 1 pointer, 1 point, 1 point, 1 point on every iterations, and on that particular iterations, what is the maximum elements in the window you have, you can return. On the very first go, you might think to use fixed size sliding window, but is it going to be helpful? So fixed size sliding window, you can eliminate something from your left, and you are going to consuming something to your right. So this problems is hard, and we are solving in life. So that means it is a kind of different problems that we have already solved. This is a kind of a different versions of it. We not going to directly do the consumption and eliminations, the template that we are learning from very past videos, because if you are doing the sliding, you are able to slide. I am not putting any doubt you not able to slide. You will be able to slide by doing a consumption to right and eliminates and L from the left. That we will definitely able to do. But the challenge is, even after you are able to slide, you have to give me the maximum of the current window. So by sliding, you are not able to make whoever is the maximum in my current window. You don't able to adjust those, right. I think you guys are getting why these problems is kind of a different of the other problems we have solved. On other problems we are able to do consumption and elimination by moving our pointers, right? But in these problems we are not able to do so, because the reason is, when we are eliminating, if let's suppose we are doing eliminations by our left pointer, and let's suppose we are doing the elimination of an elements which is the current maximum of the window, now by eliminating that particular elements, someone in after eliminating that particular elements is going to become maximum, then to find it we have to again iterate to the k size window. We again have to iterate the k size window. Like this way, your time complexity becomes n cross k, and you can see our nums dot length is as big as 10 raised to the power 5, and our k can be as big as nums dot length. So that means 10 raised to the power 5. So that means you are going to get an TLE for sure with this approach. You are going to get a TLE for sure with this approach. Now I will highly suggest take a 1 to 2 minute pause for sure and basically do some brainstorming. Think once about how you can handle this. Any thought is appreciated. Whichever you can think. Let's just put a think. That's exactly I want to see. Can it be solved by standard left and right consumption eliminations? I don't think so. Any thought if you guys can put on the comment section on this particular problem's point of view. Any thought how we can solve it? One hints I am giving. You can see this particular things 3, 3, 5, 6, 7 like this. When we have just do the slide out window from left to right, the answers we are going to get is 3, 3, 5, 7, 6. If I am going to plot it, is kind of increasing only. 3, 3, 5, 6, 7. Can you think on that particular direction? Any idea? Guys? Any idea? I know it's a hard problems, and on that reasons I am expecting massive drop of peoples. Initially we have start with good number of peoples to watch, but eventually peoples are left out because I know, because sliding window is kind of a master level variable size sliding window. If you are able to solve, then on 99% interview you might able to going to get cleared, because variable size sliding window, at least the sliding window concept is very important. It's very important on interview perspective, and specifically this variable size sliding window you can't miss. If you are preparing in top companies, you can't miss this. You can't say I don't know variable size sliding window, I don't know fixed size sliding window. You are going to propose a quadratic complexity solution, and you are going to make your doors to be very clear to becomes a rejection path on that interview for sure. I am very strictly stating you can't skip these particular topics if you are preparing for top companies for sure. So any thought guys, any thought that you can think, any thought, anyone, any kind of thinking is appreciated. Oh, nice, Manik. Very awesome. Very good. That's exactly I'm looking for. It is not a very like exact problems of the sliding window, but it is indeed a sliding window problems. You can say it, but it is rather sliding window. I have to say it's kind of a monotonous stack problems. It's indeed a monotonous stacks, and what I why I am stating this, why on that times why I am giving these hints to you guys. You can see these data points 3, 3, 5, 6, 7. So it is kind of monotonically increasing. It is a kind of monotonically increasing your answer, right? But your answer can be decreasing also, but there is an hints that is a very good hints to basically think about this, your final answer not needed to be monotonically increasing, but it is a problems of monotonous stack versions. I just quickly give you the hints why it is a problems of monotonous stacks, because it is a kind of a different versions that we are till now we have solved. So I think we definitely need a whiteboarding for sure. So focus guys now. So what we actually have, so on till now the problems that we have solved, that problems have a speciality of consumption and elimination. But here in the why I am stating this is a kind of a monotonous text. So let's consider a list. Let's suppose we have some value x, y, c, a, and you always have to, we always have to do how we have to look for by our right pointer. When we are at right pointer, we have to see, including this right, if my window is invalid, then shrink your left to some validity, that is exactly we are doing. Including my right, move your left until L2R becomes valid, right? Exactly these things we are doing, from last few videos, last few explanations, last few problems, right? So but here tell me just one thing. If we have to consider this window, let's suppose we are considering this window of size 2, right? So this particular window, now when we are basically consuming, we are basically do the consumption by our right pointer, where when we are doing the consumption, then let's suppose previously we have pushed this x to our monotonous stacks. Let's suppose any queue data structure. Let's suppose queue, because it's a double-ended queue. We can add it and eliminate it big of one time on both the side. Elimination, addition and elimination is supported in big of one. So we took a DQ. Right? Now tell me one thing. If my x is more than my y, if my x is, when we are at y and we are trying to push it to my current queue, if my x is more than my y, so are we good to push it? Because let's suppose on future, when we are going to push a z, our window becomes, let's suppose, xyz, and who is the maximum of this? X is maximum, right? X is maximum. So this is valid. When we are at y and when we are trying to push it to my dq or the queue data structure, then we have to basically first have to think, do we have to push it or not? So we only have to push when my previous elements is bigger. So then the window that we are considering, that elements can contribute to my answer, because it is still becomes the greatest elements of the window that I am considering. But let's consider the reverse case. Of it. When this is the case, when the y that we are trying to push, so this is our trying, that we are trying to push, that from this particular by our r pointer, we are just consuming this. By this, when we just consuming this particular elements, by our right pointer, and when we are basically stating, this particular y is more than some of the elements that we have already pushed, my x, which is smaller, then if I am considering a window including from this to its left, will this be ever to be a greatest elements at all? I don't think so, because we found one latest biggest elements, latest and biggest elements with the past. So again, let's suppose we got an z which is more than my y. Then we will, then do we will push this z to be as it is? No, no, no. Omit this z, omit this y, and then push this z, because this y is not going to help at all, because we have already found the latest biggest element z, right? But let's suppose we have x, y, z in this order, then we will definitely push everyone. So our q is always going to becomes monotonically decreasing in nature. It should be monotonically decreasing in nature, right? It should be monotonically decreasing in nature, right? So that is, it's a problem of monotonous stacks, more specifically I have to say, but it's a variant of sliding window. Sliding window is also needed by the consumption part, but that is how you have to basically think about it. When you are basically consuming it, you have to basically trim your queue. You basically trim your queue. You basically eliminate the queues elements which if the current elements is bigger, if the current element is bigger. So if you are standing that particular elements, and if you are basically looking to your left, including him, he is already greater. Someone tweets left and smaller, should, would it be going to make any sense? I don't think so. So they should not be in the answer considerations, and our answer considerations is running on our queue, so it should not be in part of our queue, right? I am pretty sure is kind of a little consuming this monotonous text, but we have solved multiple problems in our monotonous text on our channels. You can go through that particular problems and post that. If you have any doubt, you can just ask, just put the comments on these video sections also. We will happy to make it answered. But on high levels, I think the things is clear. What actually how actually we are building our monotonous text. When we are having some more bigger elements to be pushed to be queue, the elements which are more, we have encountered them in past, and those are in smaller, they are not making any sense. They are not making any sense at all. They are not making any sense at all, right? So that is the beauty, the games that you just have to play with it, right? So now can we quickly try to implement these things out? Can we do some quick implementation if the things is clear to you guys? If the things is clear to you guys, we can start on the implementations. I think so. It's bound to be clear with the explanations that we did. We should now going to take a queue that we have discussed. Queue should be my DQ only. We can left pointer, we don't think so we need it. We can start with our right pointer. Oh, cool, Rajan, you understood. Yeah, fine, man. Yeah, a big thumbs up. Yes. Yeah, like you have to be like on whiteboarding explanations. I did the particular problems which actually need it. So these particular problems is actually a different versions. Here you can see, right, when we will complete the entire code completions when we did, then you will get it. Like it is kind of a problems where we actually have a different from the templates. It's kind of a different what we have done in the templates, right? So that's the reasons I am repeatedly stating, like when I'm doing the whiteboarding, please focus on this. You will definitely get the things to be cleared in first go. If not on the first go, then next iterations, if you are going to get on the video on the second time, you will definitely get. Now quickly do the implementation for R in range in, right? How we have to do the consumption? We can add it. Q.append, we can add to the index. Now how we can check? So before adding, right, what we have to check for for r in range n. Rather than writing an loop, I can try this times a while loop, because for monotonous text is kind of an easy to write. So that's the reasons I am basically shifting myself to basically try to write some while kind of loop. We can follow to this. This should also work. Let's make a try, right? So this is my current elements, and we have an queue. So while my lane of queue, when we have our queue, and when we have to pop some elements from the queue, when the elements that we are trying to push, which what is the element? That is nothing but my nums of r. The elements that we are trying to push, and what is the elements that we have last pushed to the queue, that is of q of -1, and what we have pushed the index. So what is the value? Q of -1, nums of q of -1, we got the element. If the elements that we have already pushed in our queue, if it is smaller, the nums of r that we are trying to push, then we definitely have to do a q dot pop and eliminate those elements. Now that is one part, right? That is one part. And finally we have to append q dot append of whom? Q dot append of r, this index we have just ingested to our queue. Then what we have to do? We always have to take care k equals to 3. We don't have to make our window as big, which actually having more than k elements, right? Now we have to check while my lane of q, right? When we have our lane of q, and if what is the very first elements in the queue, how we can find the delta? We have pushed indexes, and what is the very early element in the queue is present in the q of 0, and what is the elements what is the current index? It's r. If r minus q of 0, so that is the L of the window. Q of 0 is the L of the window, that is the index where we have the L plus 1. If that is the window size is more than my k, do we have to shrink? Yes, man. On that particular case also you have to do. Now on this times we are shrinking from where? From which particular part? From left we are shrinking by moving our left pointer. So how we can shrink on the queue? By doing pop left for sure. Q dot pop left. Here focus on this, guys. Q dot pop left by shrinking the left part. By shrinking the left part. Clear, right, guys? Clear to everyone to you. Clear. I just want a clear to everyone. Now what is the first window which is going to be becomes valid? If my k is 3, if my r is 0, 1, 2, so if my r is more than or equals to my k minus 1, so from which index is it started valid? We have to start considering our answer. So from 0, 1, 2, that is the index. So that means when my r becomes more than my k minus 1, from this index we have just started to take some valid answer. And if that is so, do I have to push these elements to my queue? Whom I have to push? Who is the largest, including my r, to be whomever I have to push to my answer? Who is the largest elements? As it is a monotonically how it is monotonically decreasing stacks. As it is a monotonically decreasing, we have discussed, right? So which elements is the largest elements in my queue? Where it is present? Is it at the very first, or is it at the very last? Very first or very last? Why it is? It should be at very fast, because it's monotonically decreasing. Can I then push it directly to q of 0 then? Yes, we should. And finally we can return our answer. Yes, guys, this small tiny code, and it should Answer should we have to start with a list, and this should bound have the capability to give you an AC for sure. Something missed. This in should be len of my nums. Sorry, my bad. Is this beautiful code is going to give an AC? No, it's not. What happened? We are doing n equals to len of nums q. We have initialized q equals to dq. Answer equals to empty for r in range in, right? For r in range in. Anything else I am missing? While len of q, while len of q, nums of q of -1 is smaller than my nums of r, q dot pop, q dot append nums, while my len of q, r minus q of 0 plus 1 more than k, q dot pop left, r more than equals to my k minus 1, r is more than my k minus 1, then we are doing q of 0, q of 0, what do you mean? Okay, we are doing q of 0. I guess I got the work. You guys also got the work. What we did wrong here? Yes, Rajan, you are correct. We just messed up with that only. So here we have to do nums of q of 0, because q is holding indexes, but on answer we have to return the value. So nums of q of 0. Correct. So that is the work. Yes, Rajan, you are correct. Here we have to push the answer to be nums of q of 0. Yes, the sample test is passed. Quick submission. We should get an AC for sure if things are good. Boom. Yes, another AC. Another AC. Right? So we have solved another, in life we have solved another master level problems for sure. Is it clear? Is it awesome? Is it clear to you? Everyone's, if you are able to understand, please do. Yes, understand. Please put an understand here. Please put a thumbs up. Please do a subscribe. Please do. I think now though we are definitely deserving, right? With these two consecutive hard problems we did in life, right? Everyone's able to understand. Everyone, next level. Thanks, Manik. Everyone's, those who are following from very initial, very beginnings, are you guys feeling you have solved two hard problems? Have you feel ever like we are solving hard problems? Not at all. Not at all. We are solving that hard problems with this much ease. You are not able to feel at all. These are hard problems. So you have solved 1, 2, 3 and one problem here. That is the base foundational problems. So 4 problems covered. Last problems of the day that we are going to solve, that is of maximum subarray. So these problems I actually don't want to categorize this in kind of a like sliding window at all. So here basically we this is very popular problems on cadence algorithms. So on very single lines you can see, given an integer array nums, find the subarray with largest sum. So largest sum subarray is nothing but a very popular problem of cadence algorithms. So this is not at all sliding window problems that I have to say, but yeah, like for sake of simplicity, like for sake of clarity, we can quickly solve it. We just have to write the cadence code here. So I'm not going to explain much on the cadence code. Maybe we can take it on some later part, but yeah, I am not going to take some major focus on the cadence. So cadence algorithms is not like here and there with matching to the uh, sliding window at all. So here we just have to write the cadence. So on cadence we start with sum and answer. Sum we are starting with 0 and answer we are starting with sum. What is the 10 raised to the power 5 and negative can be 10 raised to the power 4. So what is the largest, like we need the maximum, but what is the very smallest minimum? So it can be 10 raised to the power 9. 2 3 4 5 6 7 8 9. So that can be my answer. Now for each in, now for each in where, now for, tell me guys, now for each in we have to iterate in nums. For each in nums, cadence we are writing. Those no cadence, please revise your cadence algorithms if it is matching to us only. If sum we are doing plus equals to each, if at any particular time my sum becomes negative, sum less than equals to 0, initialized your sum to be 0. That is cadence actually stating this. I will explain cadence in a different video. This particular video is very focused to sliding window only. If you understood all the particular things that we have discussed over the sliding window, then you should be good. But just for the sake of like clarity, to complete our DSA sheet that we have prepared, that is also our in motto. So to make the things on that path, we are just going to quickly complete this particular problems, because this is pointed as a sliding window problems in our DSA sheet. So but it is not a very straightforward, very like hard-coded sliding window problems at all, or even it's not a sliding window problems at all. It's standard cadence. Now we have to take answer equals to max of answer and sum, and finally we can return our answer. That's it, right guys? On high levels, if I remembered cadence thoroughly, then this is the things we are generally do. Maybe I am wrong, I not revise cadence. It's passing. Let's try to submit it if things are okay. Cool, we got a wrong answer. So that means we have some negative. Okay, so cadence always going to make sure that if your sum becomes, at least sum should be more than 0. Cadence should runs on negative elements for sure. Follow-ups, if you have figured out big of n solution, try coding another solution using divide and conquer approach, which is more suitable, more subtle. Okay, divide and conquer I don't think so, but on cadence I think we need one modifications, because cadence always going to make sure your answer should be within the boundary of 0 to some positive value, but here our answer can go some negative value at all. So on that case, just so when my answer, like my summations is never, my summations is going to become negative, but not every elements is going to become negative. So there should be some positive elements for sure to use cadence, right? Cadence is only going to help us when there is at least one positive elements. If there is at least one positive elements, then my maximum subarray sums becomes from this element itself. If there is only single positive element, so cadence basically work from, I think so you guys remembered, cadence basically giving you answer cadence from 0 to some positive value. So cadence basically give you some positive value, but if your answer is going to becomes negative, so that means if by cadence your answer is going to becomes negative, it's never going to becomes happen, and it's only becomes going to be happen when we have all the negative elements, so we just have to take one booleans, what I can think of to get a quick AC on this particular problems. We can take a okay boolean equals to false for each in nums if each greater than 0. So then I can do okay equals to, maybe I can do a okay equals to false, and I can take a okay equals to true here. So if I have a single positive elements, then we can apply cadence. If I have a single positive elements, then I can apply cadence. and if we have all negative, then my OK is never going to becomes true, right? And when we have found only a single positive, then we can break it also for this, because we just need to validate if all the elements are negative. If all the elements are negative, then my OK is set only, because we have set it and we have only made it false when we have only a single positive. And if my OK is true, so that means everyone's to be negative, so then can we return max of my nums? So that is the single elements. We just have to consider if everyone is negative, what is the maximum sum subarray? What is the maximum sum subarray you can get? The single elements, single negative elements, out of all the negative, who is the largest? You can return those. You can return that, right? I think now it should work for sure. Is it working? Sample to fine, passing last time also. Submission, yes, it's 84% faster, and it's, I think it's indeed an most optimized submissions, right? We have covered all. I think the problems that we 5 problems we have solved. Last one I am also putting the notes. It's not a sliding window problems, but I think the problems that we have solved is provide you a very good insight, is provide you a very good insight. If so, please do a quick like, subscribe, please do. If you feel this entire streamings that we have did is helpful to you, please do a quick like and subscribe. Please do, guys, please do. And with this note, I think we can wrap the today's sessions. With this note, I think we can wrap the today's sessions. Thanks. The congratulations signs you guys are putting, right? Are we good? Any doubt if you have, ask right away. Any doubt if you have, ask right away. I am here to you guys another 2 to 3 minutes, at max 2 to 3 minutes. If you have any doubts, you can put those, or else I am going to close it. I'm here, guys. I am here till 9:35. 9:35. I am here to you guys. If you have any doubt, not related to, thanks Rajan, thanks Manik also. Thanks, guys. Thanks those who are actually watching live to us and able to understand the things, able to understand the entire explanations, entire all the 5 problems we did, entire the templates that we have built. I will share the note to you guys in the video description, so you can find it from there, right? If you are able to understand, all things are clear, then I think we are in the very good part to wrap these sessions. I think we are in very good boat to wrap these sessions. Okay. I think we don't have any further problems, further clarifications to get clear. The sliding window entire concepts we have digested with very thoroughly, right? Okay. Thanks Manik, thanks Rajan, thanks everyone who basically liked, comment and shared, subscribed. Please share the videos to your friend circle so that they can also get most of it of this video. These are the industry level problems that we have solved in life. So yeah, I am here with 1 to 2 minutes more, but I am just going to put the streams on the ending soon mode, and I am here. If you have anything out of this sliding window, out of these topics, if you have anything top of your mind, you can, which can be like quickly addressing within 5 to 10 seconds, within 1 minute, right? Within half a minute, 1 minute, if we can quickly discuss those, you can put it. But I am just going to put the streamings that we are doing, I am putting it to the ending mode. If you have anything, so you can put it. I am here to you guys all in another 2 to 3 minutes. You can put it here. I'm put the streamings in the stream ending mode. I'm here, but I am here. So if you have anything before we are going to end it completely, you can ask those. You can ask those particular things, right?